Hello everyone, welcome back to GTC classes. So dear students, in this video we are going to see the questions that were present in the Gpat 2025 examination. This is going to be the third part of Gpat 2025 question paper analysis, and in this part, in the third part, we are going to discuss all the questions that were from the topic pharmaceutical chemistry. So we are going to discuss and all the questions from any of the pharmaceutical chemistry portions, either it is medicinal chemistry, analysis, organic, inorganic, physical, all of those questions will be discussed in this part. So let's get started with the first question. Question number 76. The question was, arrange the following alkenes in order of its stability. When we are talking about the stability of alkenes, that is totally decided by the hyperconjugation. So the hyperconjugation tells us more the number of alpha hydrogens, more stable that particular alkene is going to be. We are having cis-butene, trans-butene. Among cis and trans, we knew like trans alkenes are more stable than the cis form due to steric strains. So trans will be more stable. This option is wrong. Okay. Trans-butene must be more stable than the cis-butene. So here that is okay, and that is also okay. What about the other one? We are having 1-butene. So 1-butene will be having just 2 alpha hydrogens. 1-butene will be something like this. That is having CH2, CH3. So this is your 1-butene, this is alkene, and in the alkene segment we are having just 2 alpha hydrogens on the alpha carbon. So this is having just 2 alpha hydrogens, while in the case of trans and cis butenes, it will be having 6 alpha hydrogens. It means the least stable will be 1-butene. So 1-butene, 1-butene, 1-butene. Now the only left option is like isobutene. Isobutene structure is something like this. We are having that is having CH2, double bond C, CH3 and CH3. So this is our isobutene. This structure is also having 6 alpha hydrogens, same that were present in the case of trans-butene and cis-butene. But in the isobutene, all the 6 alpha hydrogens are present only and only on the single alkene carbon, while in the case of cis and trans, the 6 alpha hydrogens were divided between 2 carbons of the alkene. So that is why we knew, according to the hyperconjugation rule, if we are having same number of alpha hydrogens, so we have to check like if those alpha hydrogens are at cis or trans position. Okay, if cis and trans we have solved, then we have to look for the case if all the alpha hydrogens are present on only a single double bonded carbon, that will be more stable. So isobutene will be more stabilized. So D is the correct answer. D is going to be our correct answer. So D is the right answer of this question. Okay. Pyridine is a base with Kb equals to. So it's a direct question. You have to just memorize the value. 3.8 into 10 power minus 7, 1.7 into 10 power minus 12, 3.2 into 10 power minus 6, or 2.3 into 10 to the power minus 9. So the value exact is going to be 10 to the power minus 9. Only this option is having that value. So we are having the right answer of 2.3 into 10 to the power minus 9. So this is the question number 77, and according to this, the Kb value of pyridine is around 2.3 into 10 to the power minus 9. Next question is question number 78. Which technique is employed for the location of radioactive isotopes in biological and other materials by using X-ray sensitive film? Is it sequential analysis, autoradiography, precursor product sequence, or liquid scintillation counter? So the right answer for this question is going to be autoradiography. That is autoradiography. So the right answer is autoradiography. The technique employed for the location of radioactive isotope in a biological and other material using X-ray sensitive film is known as autoradiography. This autoradiography, in this a sample containing radioactive isotope is placed in contact with the X-ray sensitive film or a photographic emulsion. So this is how this technique works. So the right answer is autoradiography. Question number 79. The question number 79 is asking like cis trans EZ isomerism is exhibited all except. We are having few options here. All of them are showing cis trans or EZ. You can simply say like geometrical isomerism, except one of those option is not showing this geometrical isomerism. 2-chloro 3-hexene is showing this geometrical isomerism. 2-chloro 3-hexene, reason like we are having CH3, 3 is having hexene. Okay, so CHCl, CH double bond CH, CH2, CH3. So this is 2-chloro 3-hexene. Yes, this structure is having restricted rotation. All the atoms on a single double bonded carbons are different. So yes, this is showing 1-butene. Not possible for 1-butene to show GI, since the double bonded carbon is having two same groups. If we are having two same groups attached, then this cannot show GI. So this is not cis trans or EZ isomers. 4-chloro 3-pentene will be going to show like second carbon is having double bond. The double bond is between second and third. So yes, that will be having the case for the GI. 2-butene 1-ol is also having this GI. Reason, look at the structure. We are having 4 carbon. In the first carbon, we are having OH. So CH2OH, and at the double bond is around second and third carbon. So this is the structure. So yes, that is also having GI. Okay. So only and only 1-butene is not having tendency to show geometrical isomerism, not showing geometrical isomerism. Question number 80. Alkyl halides are converted into alkanes by. So we are having alkyl halides and that is converted into alkanes. Birch reduction, Grignard reagent, Sabatier-Sandens reaction, or Wurtz reaction. So alkyl halide, that is an RX, when reacted with sodium metal, it shows coupling like reaction. Both the alkyl chains are joined and we are having a alkane system. So this reaction is known as Wurtz reaction. So the correct answer for this question will be D, that is Wurtz reaction is the right answer. Except them, Wurtz, that is when sodium is reacted with alkyl halides in dry ether, it gives us alkane. Birch reduction reaction, it is a reaction of the alkyne system in which we are having sodium or lithium metal when dissolved in liquid ammonia is reacted with alkyne, we are getting a trans-alkene. System. We have to remember like the reagent is sodium or lithium metal in a liquid ammonia. When the hydrogenation reaction taking place on an alkene in the presence of these reagent, we always get the trans-alkene. And if we are having palladium poisoned with barium sulfate or palladium poisoned with calcium carbonate, that is also known as Lindlar catalyst, we always get the cis-alkene system. Grignard reagent, that is the reaction of carbonyl compounds. When carbonyl compounds is reacted with the alkyl magnesium halide, we get a addition, nucleophilic addition kind of reaction, and we get the alcohols. Okay, alcohols. The next one is Sabatier-Sandens reaction, that is also known as hydrogenation of alkenes. System. Next question is, that is 81, that is benzene undergoes a Friedel-Crafts reaction with isopropyl bromide in the presence of anhydrous aluminum chloride catalyst to give. We are having benzene when reacted with Friedel-Crafts reaction with isopropyl bromide. So it's an electrophilic aromatic substitution reaction. It is taking place only in the presence of a Lewis acid catalyst, that is, let's suppose it's AlCl3. So we are having this AlCl3 when reacted with Br, we are having a CH3, CH positive, CH3. This is the electrophile that we obtain by the reaction of them, and we are having AlCl3, Br minus. So this is what the catalyst does. And this is your attacking reagent. Now this attacks on the benzene ring, and the product that you are going to get will be CH, CH3 and CH3. So this is the isopropyl bromide. You are going to get the isopropyl benzene. So B option will be the right. Isopropyl bromide was our reagent. Okay. So B is the correct answer. That is isopropyl benzene we are going to get in the product. Question number 82. N-butane exists in how many number of conformational isomers? We are having N-butane. Now this N-butane can exist in two forms. Okay, this N-butane can exist in two forms. This one, that is known as, you can say it's a eclipsed form. This is eclipsed form, and this is known as Gauss form. This is known as Gauss form. So CH3 H CH3 H. Now after rotation we obtain various other Gauss and this eclipsed form that we are going to name them separately. That is, this is your Gauss form. After rotation, after the next rotation, we will be getting like this is CH3 is H and CH3 H. Okay, further rotation we will be getting this CH3 here, H, CH3 here, H. This is the anti-form. Only one anti-form is possible. After the next rotation, we will be getting this CH3 H, CH3 H. This, and the next rotation, after the next rotation, we will be getting something like this structure, that is CH3 is here, H. Okay, so one anti, two anti is not at all possible. Only one of the anti form is possible when both the methyl are at the 180 degree opposite to each other. Only one anti is possible. One anti here, one anti here. Only one Gauss or two Gauss system we are getting. So my dear, look, this is the Gauss system. Okay, this is the Gauss system. Sorry, here one Gauss is this one where both the methyls are far from each other. This is the Gauss one where both the methyls are far from each other. While here you can see CH3 is overlapping with hydrogen. CH3 is just placed above the hydrogen. CH3 hydrogen, and this one was anti. This is anti. CH3 is placed on the CH3. This is known as fully eclipsed. This is Gauss, Here, this is partial eclipsed, that is partial eclipsed, PE, partially eclipsed. This is also partially eclipsed. And this was anti. So we are getting one anti and two Gauss system. Yes, that is correct. So the right answer will be A. One anti form and two Gauss forms will be obtained after the various conformations, rotations of this N-butane structure. Okay.
Identify the naturally occurring pilocarbon. So asking about the pilocarbon, that is the drug, and the option says 2R 4R pilocarbon, 3R 4S, 2S 5R and 3S 4R. So basically they are asking about the rotation, okay, the position of that rotation and what particular type of rotation is that, whether it is a sinister or the rectus, right side or the left side. So let's look on to the structure of the pilocarpine first, and before that, the pilocarpine is a naturally occurring, okay, it is basically obtained from the leaflets of the Pilocarpus zebrandi and the Pilocarpus microphyllus. Now if we look on to the structure, the numbering starts from 1, 2, 3, 4 and 5th, okay. Now we can see at 3rd and 4th position we have the rotatable bonds, okay. So the position of the rotatable bond is at 3rd and 4th position. So if we look on to the options, A says 2 and 4, not at 2nd position, we don't have, removed from the list of the options. Then at B it says 3 and 4, yes, at 3 and 4 we have. C says 2 and 5, this also can be removed. At 5th and 2nd we don't have any rotatable bond. At D it says 3S and 4R. So B and D, from that one will be the answer. Now if we look on to the 3rd carbon, starting with the 3rd one, so this is the 3rd carbon. Here at this side we have one attachment, here we have the 2nd attachment, and this nitrogen here is the 3rd attachment, and there is one hydrogen. Now remember that hydrogen here is at towards the towards us, the hydrogen is there, that is towards the plane, not behind the plane, the hydrogen is there. So priority is starting from oxygen, then nitrogen, then 3rd. Now you have to remember one thing, that whenever the hydrogen is towards us or whenever is above the plane, the hydrogen is there, at that time whatever our answer will come or whatever the result will be there, if there will be R as a result, then we have to take the result as a opposite, means the result will be S, and if there will be S, then we have to take the opposite result, that means R, okay. So the rotation is the clockwise rotation, means the result is coming R, that is the rectus side. Now as the hydrogen is towards or the above the plane, so the result we have to take the opposite that is coming. So the 3 at 3rd position we have the sinister, so 3S. Then next we have the 4th position. Now at 4th position, this is the carbon. At one side we have oxygen, at one side we have the nitrogen, at one side we have the CH3 group. Now here the hydrogen is away from the plane, behind the plane, okay. So at this time we don't have to change our result, we have to take whatever that is coming. So first priority to oxygen, 2nd to nitrogen, 3rd to this group. So right side rotation means R. So 4th position R, that is the rectus one, the right side rotation. So the answer is the D option, 3S 4R pilocarpine.
Question number 84. Total number of stereoisomers for 3-bromo, 2-butanol. We are having 3-bromo, 2-butanol, okay, OH, H, and 3 we are having bromine, and this. So we are having one chiral center here, one chiral center here. There is no any plane of symmetry, so we are directly applying the formula to the power n. That is, n is giving you the number of chiral center and number of stereo centers. So we are having one stereo center and one stereo center, that is 2 to the power 2, that will be 4. So the total number of stereoisomers will be 4. Total number of stereoisomers in this structure is going to be 4. Okay, direct answer. The
next question we have, the ring juncture or the backbone carbon in the 5-alpha cholesterol molecule is. Talking about the 5-alpha cholesterol molecule, okay. So cholesterol, basically it has the steroid moiety. Steroid moiety means 4 rings are attached to each other. Out of those 3 rings, they are of phenanthrene, and 1 ring, that is 5-membered ring, that is cyclopentane attached to that phenanthrene ring. Now they are asking about the ring juncture in that, okay. What are ring junction? The junction is basically the point where the 2 rings are joining, that is called as ring juncture. So if we look onto the structure, so this is the basic moiety of steroid, which is also present in cholesterol molecule. Okay, now if we talk about the ring junctions here, we have 3 ring junctions, 1, 2 and 3. And what is the position or the carbon that are involved in that junction? 5th, 10th, 9th, 8th, 9th, 13th and 14th. Okay, so 6 carbons are involved in the junction and 3 junctions are there. So the answer will be the C1, 5, 8, 9, 10, 13 and 14. Okay.
The question in Gpat 2025, they have asked the lambda max related to the molecule, that is morphine. Morphine shows the absorbance of UV light at wavelength, because if you observe the morphine molecule, it is going to be a 5 fused ring structure, right? So in this you cannot apply any type of the Woodward-Fieser rules or like that, because all this comes under the class of aromatic compound if it is. But aromatic compounds also, if you see according to the Woodward-Fieser rule, okay, so the conjugation it is more than 4, then you cannot apply the Woodward-Fieser rule also. Then again some other rules are also applicable. But if you observe the morphine structure, it is going to be a fused ring structure. Okay, so thereby you cannot calculate only the basic aromatic structure. Okay, whatever it is there, that is going to be considered only. So with that we can take the help of which are going to have a lambda max in and around 285 nanometer only. Okay, so generally morphine exhibits this UV light absorption because it is a unsaturated molecule and it is having a chromophore also. But with calculation part means whenever Gpat questions are related in the view of the Woodward-Fieser rule, we are going to see the conjugations which are less than 4. Okay, and if the conjugation is more than 4, you need to apply the Fischer-Kuhn rule. But there also we are going to see the different pattern of this. But in this case we cannot apply that rules. That's why whatever the nanometer or whatever the UV absorbance it is going to be there. So according to the pharmacopoeia, we are need to take that, and the absorbance whatever it is present due to this aromatic ring. Okay, so in this morphine structure, if you observe, due to this phenolic ring, because OH it is also attached, due to the phenolic ring mostly it is going to exhibit in between 280 to 290 nanometer. Exactly, if you take the 285 nanometer in most of the instruments you are going to get it. So this is how the morphine it is going to show the UV absorption in the aqueous solution. So the options, if you observe in the options, they have given 286, 266, 276, 256. So in and around 280 to 290 nanometers means option A it is going to be the right answer. Okay, so let us move to the next question. The stationary phase, okay, related to the chromatography. The stationary phase used in the steroid separations by paper chromatography. Okay, in chromatography we have so many techniques: HPLC, ion exchange chromatography, GC, TLC, but the question related here, that is paper chromatography. But actually this is a dropped question because it is having the multiple answers. The stationary phase used in the steroids, especially whenever we are want to separate the steroids by using the paper chromatography, what is the preferred one? Okay, let us see the options: acetylated paper, silica paper, carboxyl paper, Kieselguhr paper. Okay, and silica paper anyhow it is not going to be used, we know that, and the carboxyl paper it is also not going to be used. The two options, if you see, the acetylated paper and Kieselguhr paper, these two are going to be selected in case of the steroid separations. So if you select A or D, any option, it is going to be the correct one, because it is having the multiple answer. This question has been dropped and you will get the marks anyhow. So let us see some of the other stationary phases which are going to be explained. That means in case of the paper chromatography, whenever we are going to see, okay, the paper chromatography where you are going to observe different types of the stationary phases used. Carboxyl papers, Especially they are going to be used for the cationic separation of the protonated amines and amino acids. Okay, and in case of the estellated papers, so whenever estellated papers are preferred means majorly in case of the reverse phase chromatography. Okay, lipophilic substances like steroids, insecticides and pigments are also going to be separated, and Kieselguhr papers, aluminum papers, silica papers, these are going to be used in case of the steroids, that means fatty acids, low polarity substances, majorly low polarity substances, triglycerides, vitamins and pesticides. Okay, in the options we have seen the silica papers also, right? And ion exchange papers are also there, which are especially for the ion exchange paper chromatography, exchange of the ions it is going to take place, but very rarely we are going to use this. And according to the given question, if you observe, both A and D are also right. So that's why this question has been dropped. And you can refer the topic related to this in the textbooks also, wherever these are available. And if you see the options, estellated paper, silica paper, Kieselguhr paper, these three options are going to be taken into consideration. Okay.
Question number 88. Which of the following is an exception to Markovnikov's rules? Markovnikov's rule is only and only limited to the addition. When we add the electrophilic reagent on a double bonded system, the electrophilic part of our reagent is added to that double bonded carbon atom that is having greater number of hydrogens, you can say, that is having greater number of hydrogens. And now this is oppositely done in the case of anti-Markovnikov. When we apply peroxide, the case when HBr is added in the presence of peroxide, then this is totally opposite. The electrophilic part of our reagent is added to that double bonded system that is having lesser number of hydrogens, lesser number of hydrogens. So addition of HCl, no, it is only and only limited to HBr. No. HBr only in the presence of a peroxide. Only in the presence of a peroxide. That is also known as peroxide effect or Kharas effect. That is also known as peroxide effect or Kharas effect. So this is the right answer. Look, this is your propene. If we are adding HBr, without any peroxide presence, the electrophilic part of a reagent, that is H plus, will be added to that double bonded carbon that is having greater number of hydrogen atoms. This carbon is having one hydrogen, this is having two hydrogens. So H will be added to this carbon and it becomes CH3, while the Br will be added to this carbon that is having the lesser number of hydrogens. Okay, Br minus. Question number 89. Debye is the unit for measuring. Debye is the unit for measuring when two of the dipoles are separated by a distance d. Both of them are having some charges. So this Q into D, that is known as dipole moment. And to measure the dipole moment, its unit is debye. Okay, so this dipole moment is measured in debye. So debye is the measurement of dipole moment. Okay, dipole moment.
So let us move to the next question. While performing the conductometric titrations for the estimation of the acetic acid, we know that acetic acid is a weak acid. So here what we are going to do, that is conductometric titration. What is the titrant? 0.1 molar sodium hydroxide, very strong base. It is a weak acid, whereas this is a strong base, right? So weak acid versus strong base, we are performing the conductometric titration after complete neutralization of the acetic acid. That means acetic acid, whenever we are going to see by conductometry, means we are going to observe the CH3COO minus plus H plus ions. So you are going to see the acetic acid complete neutralization is going to be done by the OH minus ions. Further addition of the titrant, okay, when the end point has been reached, so still we are going to add the titrant. That means still we are going to add the OH minus ions. So what happens to the titration curve? Let us see the options. No change in the conductance of the solution. How it could be? OH minus ions are going to be having very good conductivity values. So obviously option A, it is not at all the right answer. Increase in the conductance, definitely option B, it is going to be the correct one. Color changes, oh, color, nowhere the color it is going to be impacted. Okay, color, even though it is colored solution also, we cannot say that by conductometry that is going to be the end point. Decrease in the conductance, it is not going to happen because we are adding the OH minus ions here. OH minus ions, definitely they are the good conductors. So the curve, whatever the titration curve it is there, definitely it will increase in the conductivity. Okay, so if you observe the graph related to this, curve, if you observe the conductivity, volume of the NaOH we have taken, that is a strong base, and the conductance they have been taken on the y-axis. Initially, due to the presence of these acetate ions are there, we are going to see the decrease in the conductivity. Okay, so afterwards, that means whenever the end point has been reached, then you are going to see all the acetate ions have been consumed. Thereby, you are going to see the addition of the OH minus ions, it is going to cause the rise in the conductance value. So that's why after the end point, again you are going to see increase in the conductance value. So the intersection point, it is going to be taken as the end point. Okay, so that's why whenever strong bases or strong acids are going to be used as titrants, you are going to see the V-shaped type of the titration curves in conductometry. Okay, the intersection point we are going to consider as the end point. So definitely due to the strong bases or strong acids, whenever we are going to use, the conductance value will get increase. Okay, so this is a clear explanation, you can get it, and not only from the textbooks, you can also see the Gpat mantra book also, you can refer that third edition, it is going to have all the clear explanations related to the previous year question papers. Okay, so from 2017 to 2025, this has been newly included in the third edition. You are going to see for all the previous year question papers with clear explanation. The book is Gpat mantra book. Okay, let us move to the next question. Which of the following indicator which is not used in complexometric titrations? Oh, complexometric titrations. The question just now we have seen related to the potentiometry. Now it is related to the complexometric titrations. The options, let us see: chalcone mixture, ferroin, modern black 2 and xylenol orange. Okay, so by seeing the options itself, we can identify what is the indicator which is not used. Ferroin, iron containing these indicators are not going to be used in the complexometric titrations. Wherever you are going to use in the complexometry means the suitable indicators are definitely these are going to be identified with a different names, right? Like modern black 2, solochrome black T, murexide. So these are a separate class of the complexometric indicators. These are also called as PM indicators, metal ion indicators. Okay, so let us see what are the different types of the other indicators are also, because ferrion not at all used. Only the complexometry indicators like modern black 2, erichrome black T, solochrome black T, these are going to be used in case of the complexometric titrations. Especially modern black 2 means below 6.3 and erichrome black T means above highly basic side we are going to use, and you are going to see the red color at the end point. Okay, and whenever we are going to see the murexide especially calcium estimations we are going to use at the high basic pH, and you are going to see the reddish violet color to the blue violet color. And xylenol orange, this is also there in the question. This is especially used for the estimation of some of the metals like bismuth, lead, zinc, cadmium and mercury, but mostly you are going to see in case of the highly acidic as well as neutral pH also. And whenever zinc it is going to be used, it can be used at towards mild alkaline pH also. Okay, so this is going to give you the xylenol orange. Acid you are going to see yellow color, whereas in the alkaline pH you are going to see the red color. And finally you are going to have the another indicator, that is chalcone mixture. Okay, so chalcone mixture, this is also going to be used in the complexometric titrations. This is the chemical name, that is it is sodium 2 hydroxy 1 2 hydroxy 1 naphthyl azo naphthalene 4 sulfonate. Okay, so it is a going to give you the purple to red color end point. And the other name for this chalcone mixture is also modern black 17, okay, or solochrome dark blue, it is going to call it as. And from the given options you can say that the chalcone mixture, it is also a complexometric indicator. Modern black 2 and xylenol orange, these three related to the complexometric titrations, whereas ferroin, it is not going to be used in the complexometric.
Next we have the question, sedative hypnotic barbiturates are having pKa value in the range of. So they are talking about barbiturates. Barbiturates, that is a drug that is used for sedatives and hypnotic action. Okay, now barbiturate is derived from barbituric acid, and this barbiturate is somewhat acidic in nature. Okay, and acidic in nature, but not a strong one, but a weak acid. Okay, and the pKa value of this is particularly in the range 7.6 to 8.4. Okay, so the answer is the A1. Here you can check the explanation. Basically the hypnotic and sedative nature of that barbiturate is due to the acidity that it have, and it is very weakly acidic in nature, not the strong acid.
Question number 93. Aryl fluorides can be obtained from a controlled thermal decomposition of dry aryl diazonium fluoroborates in the following reaction. We are having a diazonium salt N2 plus Cl minus. When this is reacted with HbF4 minus, what we are going to get? We are going to get what? Aryl fluorides. We are getting aryl fluoride. The only reaction through which we can synthesize are this fluorobenzene. This reaction is known as, Ball-Schiemann reaction. This reaction is known as Ball-Schiemann reaction. Okay, Gattermann reaction, that is also the case for the this N2 plus Cl minus, that is diazonium salt. But that is for the preparation of other halobenzenes, that is not for the fluorobenzenes. Gomberg reaction is the coupling of two benzene rings. N2Cl, when reacts with the benzene, the both aryl rings are getting coupled, and this is the Gomberg reaction. Sandmeyer, same like Gattermann. In this we are using, in the Gattermann we are using copper powder, and in this Sandmeyer we are using copper halide. Okay, so we are getting halobenzene here, The difference is, in this reaction we use copper powder, in this we are using copper halides. Okay, so the right answer will be Ball-Schiemann reaction. Okay, Gomberg reaction, it is for the aryl couplings. When this N2Cl, that is aryl diazonium salt, is reacted with benzene, we are getting two benzenes coupled. In the Sandmeyer we use copper halide. In the Gattermann we use that is copper powder. Question number 94. Which of the following will be most easily diazotized? Which is more easily diazotized reactions? So, suppose we are having this 1 degree aromatic amine, that is aniline. This aniline, when reacted with HNO2 or NaNO2 in the presence of an acid, let's suppose HCl or H2SO4, at temperature 0 degree centigrade to 5 degree centigrade, we get aryl diazonium salt. N2 plus Cl minus if we use as HCl, and suppose we have used H2SO4, so then we are getting N2 plus HSO4 minus. Okay, depending on the case. If we are using H2SO4, then we get this diazonium salt. If we are using HCl, then we are getting this kind of diazonium salt. So which will be more easily diazotized? We are having bromoaniline, nitroaniline, aniline or chloroaniline. These all the cases of bromo, nitro or chloro, we can see all of these substituents is going to reduce the electrophilic, reduce the electron density of the nitrogen. All of them are deactivating reagents. They are deactivators. They are ring deactivators. So only aniline is going to give this reaction very fast, very fast. So C is the right answer. C will be the correct answer for this question. C will be the correct answer.
Next we have is the question, the structural hybrid of meperidine and methadone is. So they are asking about the structural hybrid of what? Meperidine and methadone. Now this particular question from 2025 Gpat, it is the dropped question. Now why it is dropped? Because this particular question should have two answers. One should be of the structural hybrid of meperidine, one of methadone, as they have different structures from each other. Okay, but as the Gpat is the computer based question, okay, the computer based exam is that, so we can only select one question, one answer, but it has two answers. Okay, so this question was basically dropped. Now let me tell you what are the structural hybrids. So this is the basic moiety in the meperidine, and in this meperidine, when this R is taken as CH3, that becomes meperidine, and if that R is taken as this particular bulky moiety with the two phenyl groups, a CN group and the carbon chain, now that becomes diphenoxylate. Okay, so that is, they two are the structural hybrids. Now if we go on to methadone, now in the structure of methadone also, here we have a dimethylamine and here we have this particular moiety, that is the change, and rest of the structure have a similarity. So they are structural hybrids. Which two? The methadone and the loperamide, and the meperidine and the diphenoxylate. Okay, so the answer to this is A plus D. Okay, so A and D both are the answer. Next question again, methotrexate is a classic anti-metabolite. So methotrexate is an anti-metabolite drug. Okay, anti-metabolite drug of folic acid is structurally derived by N-methylation of the para-amino-benzoic acid residue. Okay, now in that they are saying that, and the replacement of pyridine hydroxyl by the following biosteric group. So what replacement, now in the structure of this folic acid, what replacement we will add at the pyridine hydroxyl group, that it becomes methotrexate. Okay, that they are asking whether it is CF, CH3, NH2 or SH. So let's look on to the structure first. So this is the structure of folic acid. Okay, now in the structure of folic acid, here we have a pyridine ring. Now in that ring, here we have a hydroxyl group. So they are asking to what group this hydroxyl group should be changed or replaced, that we get a methotrexate. So if we change it with NH2, we get a methotrexate here. Okay, so this is the answer is the NH2, that is the C option. Now the next question says the number of carbon present in pregnine is. Now pregnine, it is also a type of steroid only, it has a steroidal nucleus. Okay, now in that steroidal nucleus, at the 5-membered ring, we have some substitution attached, and based on that substitution or based on the carbon chain that is attached, we say that how many carbons are there. So in pregnine, basically 21 carbon containing group it is, or molecule it is. Let me show you the structure of pregnine. This is the structure of pregnine. Okay, and here we have a carbons attached, CH2, CH3, and total we have 21 carbons in pregnine.
Next, which of the following is not a part of the Kerr-Fisher reagent? Okay, we know that KF, that means Kerr-Fisher reagent, it is going to be used in the determination of the water content in the samples. Okay, so KF titration can be performed manually or otherwise instrumentally also, and it can be performed instrumentally means volumetric methods are also available, colorimetric methods are also available. Okay, and in this what they have asked, which is not a part of the Kerr-Fisher reagent. Let us see the options: pyrimidine, pyridine, iodine and sulfur dioxide. So if you observe the composition of the KF reagent, okay, so it contains this iodine, sulfur dioxide and pyridine. Definitely you are going to see the pyridine, iodine and sulfur dioxide. So the reaction it is going to takes place, and thereby pyrimidine, whatever the option they have given as option A, pyrimidine, it is not at all present in the KF reagent. Okay, so we know that iodine, sulfur dioxide which are going to be used, initially they are going to be dissolved in a solvent like methanol. Okay, that methanol is also free from the water content, and the KF reagent has to be everyday, need to be standardized, and we need to determine the KF factor by using the disodium tartrate dihydrate. Okay, and if you see the question, that means the KF reagent which is not the part of the one of the following, that is pyridine, iodine, sulfur dioxide, these three are present, only pyrimidine it is not related to the KF reagent. Okay, so option A is the suitable answer.
Now next, arrange the following steps in the correct order as they occur in the drug discovery process. Now in the drug discovery process, we have different steps. Now the first step in that drug discovery process is that we have to discover the target, that where the drug that will be discovered will act. Okay, so the first step is target selection. Okay, so first we have to select the target. Second, lead optimization or lead finding. So before optimization of the lead, we have to find the lead. Okay, so the second will be the lead finding and then lead optimization. So 2, 3, 1. 2, 3, 1. The C option is the right one. Okay. So this is the explanation: target selection, lead finding and then lead optimization.
Next question, if you observe, which of the following, the 100th question is also related to the pharmaceutical analysis, which of the following statement is or are correct regarding the salt bridge used in the potentiometry? Oh, again potentiometry, we have seen the second question. Already we have seen one previous question also, it is there. So this is a second question related to the potentiometry, salt bridge. Okay, so salt bridge, let us see which are the true, that means which statement it is, they are asking the true statements. First statement, if you observe, prevent the possible contamination of the reference electrode with the test solution. See, yes, that is also true. So this statement it is true. Not designed as part of the reference electrode. No, actually in the reference electrode itself we can fill the KCl solution. KCl most widely it is used as a salt bridge. Okay, so that's why if you observe some of the reference electrodes, we can fill the salt bridge solution inside there, and so this second option it is wrong. Has no effect on the liquid junction potential. Definitely it has a liquid junction potential. So obviously third option it is also not true. Definitely it has an effect on liquid junction potential. Whenever we are observing the glass electrode also it is there. So inside HCl solution will be there. Okay, as an example if you take, so whatever the junction potential it is going to develop at the tip of that bulb, it is going to make it into the zero. So that's why in the reference electrode itself we are going to have the provision to fill the KCl solution, okay, which is acting as a salt bridge. Next, mostly solidified with a 3% agar. Okay, this is also a true statement, because the KCl solution sometimes they are going to use solidify with the agar solution to the maximum of 3%. Okay, so 1 and 4, these two are true statements. So let us see the options. 3 and 4 no, 1 and 3 no, 1 is correct, but let us see 1 and 4. Yeah, 1 and 4, these are the two statements which are true. So option D it is going to be the right answer. So a primary, what is the, let us see the clear explanation, that is what actually the purpose of the salt bridge. A primary function of the salt bridge, why we are going to introduce the salt bridge solution, that is to physically separate the reference electrode from the analyte solution, okay, because we are putting the reference electrode in the solution. So in order to separate that, and it also provides, that means even though the test solution it is in contact with that, so salt bridge it is going to maintain the liquid junction potential, okay, and it prevents the direct mixing and thus contamination of the reference electrode, okay. That is one of the advantage of this salt bridge. And salt bridge is an integral part of the electrochemical cell. Electrochemical cell means whenever we are talking about, that is containing both reference electrode, indicator electrode and salt bridge, okay. So that's why salt bridge is also one of the integral part in the potentiometry, and it is going to connect the two half cells, okay, one half cell, another half cell, one half cell related to the reference and another half cell related to the indicator electrode. And a key function, that means what is the main purpose of the salt bridge, if you are talking about, it is going to be filled up with a concentrated electrolyte solution like potassium chloride, okay. So this potassium chloride, why we are going to use means in order to minimize the liquid junction potential. Whatever the junction potential created in the contact between the reference as well as test solution, it is going to maintain that, it's to almost to the zero, okay. And this salt bridge are also sometimes jellified with agar-agar solution and maximum to the level of the 3%, okay, not more than 3% it is going to be used. And that's why the statements whatever they have given 1 and 4 are seem to be correct options, okay. Let us move to the next question. The cyanide ions can be determined by nephroturbidometry as salt of the cyanide, okay. So as we all know that cyanide ions can be easily determined by ion exchange chromatography with amperometric detection. That is the most common way of determination of the cyanide ion, and the question has been given that cyanide ions can be determined with the nephroturbidometry method also. But in the nephroturbidometry, what we are going to do, mostly we are going to estimate the concentration of the substances with the solutions which are either suspensions or colloids, right. So turbidometry, turbidity should be present there, or otherwise nephrometry. So that means opalescence or any type of the precipitation you should get it by using the nephroturbidometry. So let us see the options: gold, silver, sodium, potassium. As we all know very well that in the precipitation titrations, silver nitrate it is going to be used, right. That is going to cause the precipitation at the end of the titration. So silver ions, whenever you are going to see, they definitely are going to cause some of the precipitation with any type of the anions, because Ag plus it is going to be there, it is going to bind with the anions there. So cyanide ion, it is an anion, definitely it can be determined by nephroturbidometry as a salt of cyanide. So silver cyanide, this sodium cyanide it can be formed, but sodium cyanide we cannot consider that one as a precipitate, okay. Potassium also in the same way. Gold means it is a metal, it may form or may not form. Silver is also a metal, but it is going to cause the precipitation, we know that. So that's why option B it is going to be the right answer. So in the nephroturbidometry, if you see the explanation for this question, it is going to be generally nephroturbidometry whenever we are going to use to measure the concentration of the suspended particles, right. So in case of the suspensions or colloid solutions, we are going to use the phenomena, it is going to take place by the scattering of the radiation, right. It is going to take place. Whenever the cyanide ions are present, you need a precipitate also by nephroturbidometry. So based on this cyanide determination using the turbidometry means we are going to take the help of silver ions, thereby we are going to see a precipitate with this silver ions, okay. So that's why option B it is going to be the right answer.
Now the next question of, in AB trans ring junction of steroid, hydrogen atom at 5th position has? Again the question from steroid, so the nucleus of the steroid. So they are saying in that the hydrogen at the 5th position of the trans ring, AB trans ring junction, okay, in the junction we have the 5th position, so that 5th position contains a hydrogen, and they are asking what is the configuration of that hydrogen, whether is it alpha, beta, gauss or eclipsed, okay. So whenever there is a dash bond present, that is called as for alpha, and whenever there is a solid bond, that is beta, okay. Now let me show you the structure first. So this is the structure, okay, of the steroid, and here we have a junction, and in this junction this is the 5th position, this is the 10th position, okay. Now at 5th position, if you look clearly, if you look closely, this here we have a dash bond, that means alpha bond, okay. So of the hydrogen we have what, the alpha configuration for that particular hydrogen, okay. Here you can see it more clearly, this is the 5th position, this is the junction, and here we have a dash bond, that means the alpha bond, okay. So at 5th carbon we have the alpha configuration of the hydrogen.
Question number 103. What type of reaction is diol-Selder reaction? Diol-Selder reaction, that is the category of pericyclic reaction, a cycloaddition reaction. When we are having a, if we are having a conjugated diene reacting with a dienophile, we are getting a cyclic transition state and followed by cyclic product. This reaction is a cyclic transition state derived, and we are getting a cyclic product. It's a cycloaddition reaction. It's a cycloaddition reaction in the category of pericyclic. In the category of pericyclic reaction. Okay, and this is 4 plus 2 cycloaddition. 4 electrons of this conjugated diene and 2 electrons of this dienophile are basically rearranging to give this cyclic product. So cycloaddition reaction, B will be the right answer. B will be the right answer.
Next question, which of the following masking agents? Oh, again complexometry, we got the second question. Potentiometry also we got 2 questions. Complexometry also we got 2 questions. Okay. Which of the following masking agents is used to mask the iron ion during the complexometric titration? So whenever complexometry has been performed, sometimes we require the help of either masking agents or demasking agents, right? They are going to, masking means they will prevent the unwanted reactions, okay, and demasking means whatever the hidden reactions are there, by adding the demasking agents, the reactants are will get released and they are going to participate in the reaction, okay. Let us see the given options: thioglycerol, ammonium fluoride, potassium cyanide and triethanolamine. Okay, this is also a dropped question because it is also going to contain the multiple answers. Let us see first the clear explanation for this question. What is a masking agent, how it is going to be used, like that, okay. Masking, so if you want to define the masking, means it is a process in which the substance without physical separation of it or its reaction products are going to be transformed, so such that it is physically, it is not going to be involved in any type of the chemical reaction, but it will allow the reaction to progress, right. And demasking means in which the masked substance, that means whatever the hidden reaction it is there, the substance is not allowed to react, means whenever we will add some demasking agents, then what happens, the masked substance regains its ability to enter into the particular reaction, okay. So those are the purpose of masking and demasking. Now let us see what are the interfering ions and how we are going to use the different masking agents for that. If your sample contains aluminum, iron and titanium, then ammonium fluoride, it is going to be used as a masking agent. So in the question what they have asked, iron in the form of 2, iron 2 they have given the question, right. So in that, if you observe, which of the following masking agent used to mask the iron ion during the complexometric titration? So we can say that ammonium fluoride, it is going to be the right answer. But let us see the other options: thioglycerol, potassium cyanide and triethanolamine. This is also there. So if you observe with this table, aluminum, iron, titanium are there, then ammonium fluoride we can use, as well as if you observe the aluminum iron, then triethanolamine, this can also be used as a masking agent. And ferric containing compounds, if these are there, then you can use the ascorbic acid and ferrocyanide as the masking agents. And if your metals, any metals types of the compounds are getting interfere in the chemical reaction like cadmium, zinc, arsenic and antimony, tin, lead and bismuth, then you can use the dimercaprol. Okay, in the basic solution, if you use the dimercaprol, you can mask the reaction. And mercury, if the mercury is especially interfering ion, potassium iodide, it is going to mask that. And aluminum, titanium and styrene you can use. Silver, other metals like silver, copper, iron, zinc, cadmium, cobalt, nickel and mercury also. Potassium cyanide in the alkaline medium. Okay, so these are the different agents we can use as masking and demasking agents, so that the chemical reaction, it is going to takes place, the complexometry will proceed further, right? So in this, if you observe the question, that is masking agent for the iron means ammonium fluoride is also right, as well as triethanolamine, it is also the correct option. So that's why this is a dropped question in the Gpat 2025. Okay, so all these clear explanations we have given in the textbook of pharmaceutical analysis 5th edition, complexometric titration, page number 22.11. you can observe this. And Gpat mantra book also, you are going to find all these clear explanation for all the previous year question papers. Let us move to the next question. Oh, in Gpat 2025 from the analysis, more than 10 questions they have asked. Okay, let us see the next question. The indicator involved in the Fazan's method, very very simple question it is. We know that the Fazan's method is a precipitation titration. Just now we have discussed that silver ions are going to be reacting with the some of the anions and they are going to give the precipitation. Similarly, in the Fazan's method also, we are going to estimate the chloride ions by using the silver nitrate itself. But what is the reagent indicator? What is the indicator we can use especially for the Fazan's method? So we know that Fazan's method is an adsorption indicator method. Okay, it is a direct method, but whatever the indicators we are going to use in these Fazan's method, these are acting by adsorption method. They are going to get adsorbed on the surface of the silver. Okay, so examples for the adsorption indicators are dichlorofluorescein, fluorescein, eosin, rhodamine. So all these are examples of the adsorption indicator. So dichlorofluorescein, it is there in the option A itself. So definitely it is going to be the right answer. Whereas methyl red, phenolphthalein, xylene orange, these are not related to the precipitation type indicators. Okay. So if you observe the other methods of the precipitation titrations, like Moore's method, it's a direct method where we are going to use the determination of the halides, okay, like chlorides and bromides, but not iodides cannot be estimated by the Moore's method, and chlorides and bromides we can estimate. And here the reaction, it is going to place like the silver nitrate and sodium chloride, silver chloride, which is a precipitate. Okay, and here if you observe the indicator, that is potassium chromate we are going to use, which will produce the reddish brown color precipitate. Whereas in the Volhart's method majorly it is a back titration method. Mostly the solutions which are acidic in the nature, we are going to use this Volhart's method, and this is also can be used for the all types of the halides. And in this iron containing indicators, okay, like ferric ammonium sulfate, so these are types of the iron containing indicators are going to be used, which will produce a red color complex. That means we are going to estimate the endpoint by using these types of the ferric containing indicators will produce the red colored complex at the endpoint. Okay, and Fazan's method, it's an adsorption indicator method where we can determine these halides, all these halides can react with this, but here you are going to use different types of the indicators by adsorption phenomena. Acidic dyes as well as basic dyes. Acidic dyes means like eosin and dichlorofluorescein, which are going to be used, and fluorescein, it is also one of that. They are going to be basic dyes means rhodamine, rose bengal, all these. That means dyes, basically the colors which are in the form of dyes they are going to use, okay. And adsorption, it is the phenomena, it is going to takes place, okay. And in the all the textbooks also you are going to find this instrument, fundamentals of the analytical chemistry.
Question number 106, Walden inversion is associated with. So the Walden inversion is associated with elimination reaction, SN1 reaction, SN2 reaction, both SN1 and SN2 reaction. Suppose elimination reaction, we are having elimination, that is only having the Sadjeff product. We are having Sadjeff or Hoffman rule. No any SN inversions is happening on the eliminations. SN1 reaction is having both inversion as well as retentions. Inversion as well as retention. So this is also not correct answer. Walden inversion is associated with SN2. This is having 100% inversion. 100% inversion. What inversion? That is known as Walden inversion. Walden inversion. Okay, so the SN2 is having 100% inversion, Walden inversion. SN1 having both inversion retention, so that is not the correct. C is the 100% right answer. Okay, C is the correct answer. Question number 107, how much sodium hydroxide is required to prepare a 200 ml of 0.15 molar solution? This is the molarity, this is the volume. Sodium hydroxide, that is NaOH, that is having 23, 16, 1, that is having 40. So its molar mass is 40. We knew molarity is equals to number of moles. Number of moles can also be written in the form of mass upon molar mass. Mass upon molar mass. So this is the number of moles. Number of moles present in 1 liter of solution. Volume of solution in liter. So 200 ml, that is 200 upon 1000 upon 1000. So I can write down 1000 upward. So this M we are having, W we are having. This small m is what we have to find out. Value of M is 0.15. 0.15 into this W came here, became 40, 200, 1000 here. Okay, 1 0 0 1 1 1 gone. 4 2 is 8, 8 8, that is M, what we have to find out. So 15 4 ja 60, 60 into 2, that is 12. Okay, so we are having 12, 1.2 grams. We will be having 1.2 grams. Mass will be 1.2 gram. Okay, so this will be the right answer. Question number 108. According to bare strain theory, which of the following cycloalkanes is most stable? Cyclooctane, cyclopentane, cyclobutane, or cyclopropane? So according to bare strain theory, that was totally based on strain. So according to Bayer, these all cycloalkanes are flat structures. They are flat structures, they are planar structures, and their stability order is something like this. Cyclopropane is least stable. Cyclopropane is least. More than cyclopropane stability, we are having cyclobutane. Cyclobutane is more stable than cyclopropane. Cyclohexane. According to Bayer, cyclohexane is more stable than cyclobutane, and cyclopentane is more stable than the cyclohexane. This was according to Bayer strain theory. But that was wrong by Sassamore theory. Cyclohexane became more stable. So if we are asked about the bare strain theory, so according to bare strain, we always mark our answer of cyclopentane. Octane, that is not in the case. Pentane, butane, propane. There was no any option for the cyclohexane. So no confusion left at all. So this is not correct, this is not correct. The right answer will be B, that is cyclopentane is going to be the right answer. Cyclopentane will be the.
Next question, what is the purpose of knowing the value of M in the Ilkovic equation? Okay, so the question Ilkovic equation means you are going to see the question from the polarography, right? Polarography, electroanalytical method, and let us see the options first. M, what the M indicates in the Ilkovic equation. To determine the drop time, time means it will be in the form of T. To calculate the mass of the electrons transferred, to determine the mass of the analyte, to calculate the mass flow rate of the mercury. Actually D option it is right. Let us see with explanation how the Ilkovic equation looks like, and we are going to have the clear cut part in this. The Ilkovic equation, wherever we are going to see the diffusion current, okay, limiting current, migration current, all these are going to be there. And in this Ilkovic equation used in the polarography, right? So in the polarography, that is one type of the electroanalytical method where we are going to estimate the diffusion current. This is going to be directly related to the concentration of the analyte, okay, and the concentration we can get it from the Ilkovic equation. So this is the Ilkovic equation where you are going to observe different terms. So ID means actually it is a diffusion current, okay. So ID equal to 607. 607 actually this is a factor which gives you the different parameters related to the mercury, because polarography, wherever you are going to see the type of titrations we are going to perform with the polarography means you are going to use the dropping mercury, dropping mercury electrode, it is going to be used, and in this drop time of the mercury it is going to be very important. So related to the mercury, this factor they have taken by considering the specific gravity, all the masses and everything they have clubbed into, and they have given one constant value, and N into C into D to the power of 1 by 2, M to the power of 2 by 3, and T to the power of 1 by 6, okay. So because this is somehow smaller, so that's why I have written elaborately here. So this is ID, it is nothing but the diffusion current, the average diffusion current in the microamperes we are going to get it during this drop time of the mercury, okay. And what is N? N means the number of electricity required per mole of the electrode, and what is D? C means concentration, and what is this D? The diffusion coefficient of the reducible or oxidizable substance, that means whatever the analyte it is there. And M, what is M? The question also is asking related to the M only. So what is small m? The rate of flow of mercury from the dropping mercury electrode, which is expressed in mg per second, rate of flow, okay, rate of flow of the mercury it is going to be taken. And T, small t, it is nothing but the drop time in seconds. So this is about the Ilkovic equation. So if you observe the question related to this, determine the drop time, no, M, that is actually drop time we are going to see, that is with the small t. Mass of the electrons, nowhere it is going to be there. To determine the mass of the analyte, actually we are not going to determine the mass of the analyte, we are determine the concentration, right. From the equation you can calculate the concentration. Finally the answer, to calculate the mass flow rate of the mercury, okay. So definitely this is going to be the right answer. Next, vincristin, okay, Vinca alkaloid it is. Vincristin can be analyzed by UV spectrophotometer at lambda max. So UV also they have initially they have asked for the lambda max for the morphine, which is a very complicated structure, but aromatic moiety it is present. So basic aromatic moiety means we are going to get the 285 nanometer as the parent value. So based on that we have answered that question. But now the question is Wien crystal. Wien crystal can be analyzed by UV spectrophotometry because it is a Vinca alkaloid, and we can determine this at lambda max. How we can calculate this lambda max? Actually, if you observe the options they have given 245, 217, 360, 297, all these parameters are that means all these nanometers, if you observe, these are in the UV region only. Okay, so if you observe the Wien crystal chemical structure, okay, so Wien crystal chemical structure, if you observe, you can say that this is going to be a very complicated structure. Okay, and mostly the you may not directly, that means with Woodward-Fieser rule or whatever the Fieser-Kuhn rule it is there, you cannot apply that rule to this Wien crystal complicated structure. Okay, it is a Vinca alkaloid, but we know that it is just an aromatic compound. That's what we can say. Okay, but if you observe the number of oxygens, number of nitrogens, wherever you are going to observe, very complicated structure it is going to be there. It is going to be used as anti-cancer agent. We know that chemical constituent it is, but how we can determine the lambda max? Just we can dissolve them in a suitable organic solvent, and practically we can calculate the lambda max. But theoretically, if it is an aromatic compound, we can say that okay, so and so the nanometer might be more than 285 nanometer, it might be present, right? So in that way we can guess it. But if you observe the options they have given 245, 217, 360, 297. So 245, 217, we can guess that okay, these may not be the right answer, either 297 or 360. In these two, the answer might be present. Okay, but guessing you cannot give the correct option. If you see the Wien crystal, it is a Vinca alkaloid used in the cancer chemotherapy, right? And it is going to exhibit the characteristic absorbance in the UV region. So why this aromatic moiety, it is going to be present, and nitrogen and oxygen elements are also going to be present here. And mostly you are going to see whenever energy is given to the such type of the molecules, you are going to observe the pi to pi star transitions, as well as n to pi star transitions are also going to be observed. But majorly if you observe the n to pi star and pi to pi star transitions, then mostly we are going to see that the longer wavelengths. Okay, so in the UV visible spectrophotometry, this Wien crystal, it is going to exhibit around 297, that means exactly 297 we cannot say that, more than 285, that we know that. Okay, but due to the pi to pi star transitions and n to pi star transitions, these are going to be present, definitely not more than UV, you can say that, right? And with the colored complexes, if you want to determine, you can determine by adding some coupling reagents and all these things. But as such, if you take the Wien crystal in a suitable solvent, then definitely you can estimate it at 297 nanometer. Okay, so in the given options, if you see the 297 nanometer, you can select as the right answer.
Question number 111. Energy of activation, that is EA, of thermal decomposition of glucose by first order reaction can be calculated from the y-axis intercept of Arrhenius plot, the x-axis intercept of Arrhenius plot, the slope of Arrhenius plot from a rate constant at room temperature. So this is the slope. In the Arrhenius theory or Arrhenius formula of the activation energy, that is rate constant is directly related with the activation energy. So that is the slope log 10 to the power k is equals to, what do you call it? Log 10 to the power a minus EA upon 2.303 RT, and this is what your slope tells us. So the slope is equals to minus EA upon 2.303 R if we are plotting a graph between log 10 to the power k and 1 by t. So we are getting this value of slope, that is EA upon 2.303 R in the minus, since the plot is you can see the slope is in the decline phase. So that is the right answer.
Oh, next question. almost we have crossed the 10 plus, right? In the Gpat 2025 we have observed. Okay, next question as the 112 we have seeing this. The recombination of the fragments, oh, the question related to the mass spectroscopy. The recombination of the fragments can be avoided by maintaining which of the following systems that decreases the number of collisions between the fragments or the molecules. That means whenever we will give energy, the electronic bombardment, it is going to be given in case of the mass spectrometry, which are going to cause the collisions between the ions, right? Thereby the fragmentation it is going to take place. Initially the parent ion it is going to be ionized, thereby you are going to see the parent peak or molecular ion peak, we are going to call it as. Afterwards, still if you increase the collision energy, you are going to see the formation of the different types of the ions, like daughter ions, metastable ions, different patterns are also going to be there, okay. But here what they have asked, the recombination of the fragments, recombination of those already formed fragments can be avoided. That means once ionization has been done means that is sufficient. So one ion it should not recombine with the other one, right? So it is going to give you the erroneous results. The recombination of the fragments can be avoided by maintaining. How we can avoid that? Which of the following system that decrease the number of collisions? Okay, recombination it is going to take place because of the collisions between the fragments. So what we need to do? We need to decrease those collisions between the fragments, okay. And how we can do that? That means options they have given low temperature, low pressure, high pressure and high temperature. So minimum common sense we can say that high temperature whenever we will give, automatically it will cause more collisions, okay. So obviously D option never it is going to be the right one, and some more it is actually a dropped question because it is also having the multiple answers, okay. So let us see first of all how this collisions are going to cause the refragmentation or recombination. Recombination of the fragments, whenever the fragments are going to be formed, again due to the some temperature and pressure conditions, again you are going to see the recombination of the fragments. So these recombinations between the fragments or molecules occurs due to the collisions, okay. So which are more frequent when molecules have the higher kinetic energy, right? Whenever we will give more energy to them, then obviously the collisions can be increased. And also if you maintain a low temperature, what happens generally, if you maintain a low temperature, the kinetic energy gets reduced, thereby what happen, it decrease the frequency and the energy of the collisions, it is going to take place. But this helps prevent the recombination by limiting the interactions between the fragments or the molecules, okay. That means if you decrease the temperature, automatically the collisions get reduced and the recombinations can be avoided, right. That is one option. So temperature can be low, that is one option. And another is, that is low pressure. Low pressure means while low pressure, it is going to reduce the number of molecules per unit volume, okay. Temperature it is going to reduce, low temperature it is going to reduce the kinetic energy, whereas low pressure it is going to reduce the number of molecules per the unit volume, and it is also can decrease the collision frequency. That means not directly but indirectly it is also going to have the effect on the collisions, so that the recombination of the fragments can be decreased. That is also one option. So temperature if you decrease, then also recombination can be decreased, and if you decrease the pressure also, you can decrease the recombination. And at high pressure and high temperature what happens? High pressure and high temperature, if you are talking about high pressure, this increases the number of molecules in a unit volume, right. High pressure if you are going to do, so in a given volume the number of molecules get increased, leading to more frequent collisions. So thereby the recombinations it is going to take place. And high temperature means this is also, it will increase the kinetic energy of the molecules, definitely the collisions get increased. Okay, so that's why in the given question, if you observe, they have given low temperature as well as low pressure. So both these options are correct. So that's why this question has been dropped from Gpat 2025. Okay, so in this way you are going to see the different patterns of the recombination of the fragments. Okay, so these are the, I think 12 questions have been asked in the Gpat 2025 related to the pharmaceutical analysis. Potentiometry we got 2 questions, complexometry 2 questions, conductometry 1 question, as well as polarography also 1 question we have seen, as well as mass spectrometry 1 question we have seen, and UV lambda max is also 2 questions we have seen, and precipitation titrations Fazan's method also we have seen 1 question. Okay, the indicator related to the Fazan's method, as well as all these titrometry, spectrophotometry, as well as paper chromatography also we got 1 question. Okay, so mostly you are aware of this Gpat mantra book, which is going to give you very clear explanation related to the all the previous year question papers of the Gpat. Okay, from actually 1988 to 2016 also they have included, and recently in the 3rd edition we have included from 2017 to 2025. Okay, up to that point all the previous year question papers have been well resolved, and we are giving the clear explanations in your comfort language. Thank you students, thank you for attending.